Right now, as you listen to these words, Earth is being bombarded by one of the most powerful solar events of 2025. 3 coronal mass ejections merged into a single cannibal storm and slammed into our magnetosphere just hours ago. The KP index skyrocketed to 8.67. Ground level radiation is penetrating our atmosphere. Power grid operators across 11 states received urgent warnings about voltage control problems. And somewhere deep in the calculations of space weather forecasters, a terrifying realization is taking shape. This might be the dress rehearsal for something far worse. Before we dive into what happened in the last 72 hours, hit that like button, subscribe to the channel, and hit that new hype button below. Tell me in the comments where you're listening from. Let's begin. November 9th, 2025. Sunspot region AR4274 erupted with an X 1.7 flare at 0735 UTC. Amateur astronomers watching through hydrogen alpha filters saw the brilliant white light flash across the solar disk. Within minutes, coronagraph imagery confirmed what everyone feared: a massive asymmetric halo coronal mass ejection travelling at over 800 kilometers per second, heading directly toward Earth. The transit time, approximately 48 hours, but AR4274 was just warming up. 24 hours later, on November 10th, the same region produced another eruption, X 1.2. Another full halo CME, this one even more energetic than the first, racing through the interplanetary medium at velocities exceeding the previous blast. Space weather models showed both plasma clouds barreling toward our planet, with arrival times that would place them dangerously close together. Then came November 11th, 04 UTC. The sun unleashed its fury, X 5.1, the strongest solar flare of 2025, the 6th largest of solar cycle 25. A white light flare so intense it triggered strong radio blackouts across Africa and Europe, ionizing the upper atmosphere and causing widespread signal degradation across entire continents. High-frequency communications simply vanished for up to 10 minutes in some regions. Telegraph operators in 1859 watched their equipment spark and catch fire. Today, we watched satellite communications stutter and GPS systems struggle to maintain lock. The CME from this monster flare carried an estimated billions of tons of magnetized plasma. NOAA coronagraph imagery showed the classic halo structure, the telltale sign that Earth sat directly in the firing line. But this was not just another solar storm. The 3 CMEs, launched over 3 consecutive days from the same volatile sunspot region, were travelling at different speeds. The fastest one, propelled by that X 5.1 flare, was catching up to the slower ones ahead of it. This is where solar physics gets truly fascinating and deeply concerning. When a faster CME overtakes a slower one, they do not simply pass by each other. They merge, they cannibalize. The magnetic fields interact, the plasma clouds compress, and the resulting structure becomes something far more powerful than the sum of its parts. The shock waves amplify, the magnetic field strength intensifies, and when this merged, cannibal CME strikes Earth's magnetosphere, the geomagnetic response can be catastrophic. The May 2024 superstorm was caused by a triple cannibal CME. It reached G5 levels, the highest possible classification. Auroras appeared as far south as Florida and northern Africa. Satellites were damaged. GPS systems failed. Farmers in South Dakota watched their autonomous tractors begin driving in circles, their guidance systems scrambled by the geomagnetic interference. That event cost billions in disrupted operations. Current modelling suggested the incoming CMEs would complete their cannibalization right as they reached Earth. November 12th. Today, Space Weather Prediction Center issued a G4 severe geomagnetic storm watch, not a G1 or G2, G4. The second highest level on their scale. The kind of alert that sends power grid operators scrambling to implement emergency protocols. The kind that makes satellite controllers move spacecraft to safer orbits, the kind that triggers contingency plans in telecommunications companies worldwide. But there was something else in the data. Something that made veteran space weather scientists pause and check their instruments twice. A ground-level event was underway. Let me explain why this matters. When the Sun produces an X-class flare, it does not just emit electromagnetic radiation, it accelerates particles. Protons, electrons, alpha particles, all driven to relativistic speeds by the immense magnetic reconnection events in the solar corona. These particles race across the 93 million miles between Sun and Earth in minutes, not hours, minutes. Most of the time, Earth's magnetic field deflects these particles toward the poles, where they interact with our atmosphere and create auroras. But when the particle flux is intense enough, when the energies are high enough, something remarkable and dangerous happens. The particles penetrate all the way to the ground. Neutron monitors around the world, specialized detectors designed to measure cosmic ray flux, begin registering massive spikes. This is called a ground-level event, a GLE. GLEs are rare. They happen perhaps once or twice per solar cycle. The last significant one occurred in 2012, during solar cycle 24. Before that, you have to go back years, sometimes decades. They require extraordinary solar activity. They represent particle energy so high that our planet's protective magnetic bubble cannot fully shield us. Professor Clive Dyer of the Surrey Space Centre called this event very significant. Neutron monitors detected it globally. From high-latitude stations in the Arctic to equatorial installations, the signature was unmistakable. Energetic protons, accelerated by that X 5.1 flare, were penetrating Earth's atmosphere and reaching the surface. For most people, this sounds abstract. Particles, radiation, numbers on scientific instruments. But consider what this means. These particles were powerful enough to punch through the magnetosphere, through the thermosphere, through the mesosphere and stratosphere, all the way down to sea level. They were hitting us, right now. As the CMEs raced toward Earth, a fusillade of near-light-speed particles had already arrived, creating a radiation environment in the upper atmosphere that Hong Kong companies had to account for. Polar route flights received warnings. Astronauts on the International Space Station moved to better shielded areas, and satellites, those delicate machines in the void, were being bombarded with energetic particles that could flip bits in their computer memory, degrade solar panels, and cause permanent damage to sensitive electronics. The CME arrived at 0120 UTC on November 12th. The KP index, a measure of geomagnetic disturbance, shot from quiet background levels to 8.67. G4 severe geomagnetic storm conditions confirmed. Earth's magnetic field convulsed. The magnetosphere compressed on the day side, stretched on the night side, and in that compression and stretching, energy poured into the system. Currents began flowing in the ionosphere. The aurora oval expanded, and on the ground, in the buried infrastructure of modern civilization, things started to happen. Geomagnetically induced currents, GICs. This is the mechanism by which solar storms threaten power grids. When the magnetosphere is disturbed, when those currents flow overhead in the ionosphere, they induce electrical currents in any long conductor on the surface. Power transmission lines, pipelines, telecommunications cables. These are not small currents. During severe storms, they can reach hundreds of amperes, and they flow into the power grid as quasi-direct current, something transformers were never designed to handle. Transformers operate on alternating current. The magnetic fields in their cores are supposed to oscillate, rising and falling with the 60 Hz frequency of the grid. But when quasi-DC from a geomagnetic storm gets superimposed on that signal, the magnetic field in the transformer core becomes biased. It saturates. The transformer begins to draw excessive current, heating up, vibrating, releasing gases. In extreme cases, the windings overheat and fail, and when a high-voltage transformer fails, you do not simply replace it. These are bespoke pieces of infrastructure, each one built to order, taking months or years to manufacture and millions of dollars to procure. NOAA warnings specifically mentioned possible widespread voltage control problems and protective systems mistakenly tripping out key assets from the power grid. This is the nightmare scenario. Not that a solar storm directly destroys equipment, though it can, but that it triggers a cascade. One transformer goes offline, the load redistributes to others, they become stressed, more protective systems trip, more load redistributes, and suddenly you have rolling blackouts, grid instability, and operators struggling to prevent a total collapse. 11 states received power grid warnings. The Space Weather Prediction Center emphasized that detrimental impacts to critical infrastructure technology are possible, but mitigation is possible. That last phrase carries enormous weight. Mitigation is possible if you know the storm is coming, if you have time to prepare, if operators can shed load, reroute power, take vulnerable transformers offline temporarily. But all of that requires advance warning and coordinated response. The auroras, of course, were spectacular. Social media exploded with images, brilliant greens and reds and purples dancing across skies as far south as Texas, Alabama, Georgia. Reports came in from Ireland, from northern Germany, from Japan. The visible manifestation of billions of tons of solar plasma slamming into Earth's magnetic field at millions of miles per hour. Beautiful, awe-inspiring. And for those who understand the physics, deeply unsettling. Because this was not a G5 storm, this was G4. Severe, yes. Significant, absolutely. But not the maximum, not the worst the sun can do. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, was likely 5 to 10 times more powerful than what just hit us. Some estimates place it at negative 1750 nanoteslas. The May 2024 storm reached negative 600. Today's storm, based on preliminary magnetometer data, appears to be in the negative 400 to 500 nanotesla range. Powerful, concerning. But not Carrington-level. Think about that for a moment. We just experienced one of the strongest solar storms of this solar cycle, strong enough to trigger ground-level radiation events, strong enough to warrant G4 warnings, strong enough to paint auroras across half the planet. And it was maybe 1/5 to 1/4 the intensity of what we know the sun is capable of producing. Sunspot AR4274 is still there, still active, still Earth-facing. Its magnetic configuration, classified as beta-gamma delta, indicates continued potential for major flares. NOAA forecasters estimate an 80% chance of additional M-class flares and a 55% chance of another X-class flare in the next 48 hours. The region has not finished its tantrum. Solar wind speed measurements show velocities peaked at 735 km per second during the initial CME impact, then dropped briefly before spiking again to 679 km per second. The interplanetary magnetic field, that critical parameter that determines whether a CME effectively couples with Earth's magnetosphere, reached 60 nanoteslas at the peak. For reference, quiet conditions sit around 5 nanoteslas. The BZ component, the north-south orientation of the field, stayed predominantly southward. A southward BZ is what opens Earth's magnetic field to solar wind entry. It is the key that unlocks the door to geomagnetic storms. Satellites reported degraded operations. The increased density at low Earth orbit altitudes, caused by the thermosphere heating and expanding during the storm, created enhanced atmospheric drag. Spacecraft operators had to perform unplanned maneuvers to maintain orbital parameters. This is not theoretical. In February 2022, SpaceX lost 38 of 49 newly launched Starlink satellites to a relatively modest geomagnetic storm. The atmospheric expansion at their deployment altitude created enough drag to pull them into destructive re-entry. Today's storm was far more intense. How many satellites were affected remains to be seen, but the event will be studied for years as a case study in space weather impacts on orbital infrastructure, GPS systems experienced errors, not catastrophic failures, but degradation. Positioning accuracy suffered. Timing signals, critical for everything from financial transactions to telecommunications synchronization, showed drift. Farmers, already wary after the May 2024 incidents where tractors drove in circles, checked their equipment nervously. Airlines rerouted some polar flights to avoid enhanced radiation exposure at altitude, and in telecommunications networks, engineers monitored signal quality as the ionosphere became turbulent and unpredictable. The cannibal CME delivered its payload over the course of several hours. This was not a single sharp impact, but a prolonged bombardment as Earth passed through the merged plasma cloud. Storm conditions are expected to persist through November 13th, gradually easing from G4 to G3 to G2, and finally back to background levels. But AR4274 continues to churn. The Sun, approaching the peak of solar cycle 25, remains highly active. Every day brings new sunspot regions, new flares, new CMEs. We exist in an age of unprecedented technological dependence during a period of elevated solar activity. Our civilization runs on electricity, GPS, satellite communications, and internet connectivity. All of these systems are vulnerable to space weather. And we have just been reminded in vivid detail that the Sun holds power we can barely fathom. The storm that hit Earth today was strong enough to make headlines, strong enough to trigger emergency protocols, strong enough to send auroras dancing across half the planet. But veteran solar physicists are not breathing sighs of relief. They are looking at the data, looking at the historical record and asking a different question. Not whether we survived this storm, we did. But whether we will survive the next one, what if this was just the warm-up act? There is a document sitting in disaster preparedness offices across New Zealand that outlines what happens when a truly catastrophic solar storm strikes. Not a G4 event, not even G5, something beyond the scale. The document was finalised in December of last year, and it was put to use during the May 2024 storm when Transpower, New Zealand's national grid operator, implemented emergency protocols that reduced grid load by 30 to 40% in the hours before impact. The transformers survived, the grid held, and according to Professor Craig Roger, who helped develop those protocols, it galvanised people in decision-making roles to realise that things could have been way worse. Way worse. Let those words settle. The solar storm that just passed through our magnetosphere was powerful. Ground-level radiation, G4 conditions, auroras at unprecedented latitudes. But it was not way worse. It was not the extreme event that scientists know is coming. And when you start gaming out what a truly extreme solar storm would do to our civilization, the scenarios become almost unthinkable. Start with the power grid, not just voltage fluctuations, not just a few transformers going offline, total collapse, cascading failures across entire continental networks. The 1989 Quebec blackout lasted 12 hours and affected 6 million people. That was caused by a storm that reached negative 600 nanoteslas. The Carrington event reached negative 1750. The difference is not linear, it is exponential. Dr. Kęstutis Ikamas from Vilnius University has studied the vulnerabilities in large power networks like those in the United States and Canada. His assessment is stark. A strong geomagnetic storm could incapacitate vital systems such as electricity, water supply and telecommunications, leading to extended blackouts, communication breakdowns, and logistical paralysis. Extended blackouts, not hours, not days, months. In the worst scenarios, months. Imagine waking up tomorrow morning and the power is out. You check your phone, no signal. You try the landline, dead. You turn on your battery-powered radio and hear emergency broadcasts saying this is not a local outage, this is national, this is global. The Sun has hit us with something unprecedented, and the power grid has collapsed. Within hours, grocery stores are emptied. Not because food is scarce yet, but because without power, credit card systems do not work. Electronic registers do not work. Refrigeration does not work. People take what they can. Within days, water treatment plants fail. Pumps require electricity. Sewage systems back up. Hospitals switch to emergency generators, but those have fuel for maybe a week, maybe 2 if they are lucky. After that, life support systems go dark. Telecommunications networks collapse. Cell towers have battery backup, but only for a day or so. When those batteries die, you lose the ability to call for help, to coordinate response, to even know what is happening beyond your immediate neighborhood. The internet, that vast global network we treat as permanent infrastructure, fragments and dies. Data centers lose power, cooling systems fail, servers overheat and shut down, the cloud evaporates. GPS satellites, assuming they survive the initial radiation storm, lose ground contact. Even if they are still transmitting, the ionospheric disturbances make positioning signals unreliable. Navigation systems fail. Shipping containers pile up at ports because the automated systems that track and route them are offline. Aircraft are grounded. Not just because GPS is down, but because air traffic control systems require power, require communications, require a functioning infrastructure that no longer exists. Supply chains disintegrate. Modern logistics operate on just-in-time delivery. Food does not sit in warehouses for months. It moves constantly, from farm to distribution center to store, arriving days or sometimes hours before it is needed. When transportation stops, when trucks cannot refuel because gas station pumps require electricity, when railroads cannot operate signals, the entire system seizes up. Cities, which import nearly all their food from surrounding agricultural regions, face starvation within weeks. The financial system collapses. Banks operate on electronic ledgers. Trading floors require power and internet connectivity. Even if some institutions manage to keep generators running, the network effects doom them. If counterparties cannot confirm transactions, if clearing houses go offline, if the fundamental infrastructure of modern finance evaporates, what happens? In the chaos, what is your bank balance? How do you prove you own your house? How do you prove anything? This is not science fiction. This is not a zombie apocalypse scenario. This is a straightforward extrapolation of what happens when the technological substrate of civilization is removed. And a Carrington-level solar storm, perhaps combined with inadequate preparation, could remove it. The Swiss reinsurance company Re has estimated that 10% of all transformers would be damaged during a Carrington-class event. 10% sounds manageable, until you remember that each high-voltage transformer is a bespoke piece of art, as one engineer described them. They are not mass-produced. They are individually designed for specific substations, built to order over the course of years, and cost millions of dollars each. The United States has thousands of high-voltage transformers. If 10% fail simultaneously, you're looking at hundreds that need replacement. The global manufacturing capacity for these transformers is measured in dozens per year. Do the math. If you lose 300 transformers and can produce 30 per year, you're looking at a decade to replace them. A decade, during which large sections of the grid remain dark, during which everything that depends on electricity, which is everything, remains non-functional. Some researchers suggest the economic impact of a Carrington-level event could reach $2.6 trillion in the United States alone. That figure, compiled in a 2013 study analysing impacts on North American power grids, represents somewhere between 3.6 and 15.5% of annual GDP. The global cost, as the Planetary Society noted, is beyond the scale of our comprehension. But perhaps the economics miss the point. Money is an abstraction. What matters is water, food, medicine, shelter, and the social order that allows us to maintain these things. A prolonged blackout does not just inconvenience people, it kills them. The elderly, dependent on powered medical devices, the chronically ill requiring refrigerated medications, infants needing formula and clean water. In the summer, heat waves become deadly without air conditioning. In the winter, people freeze without heat. And throughout it all, as systems break down and resources dwindle, the social fabric frays. There are historians who study societal collapse. They look at civilizations that failed, that disappeared, that went from complexity to simplicity in the span of generations or even years. The mechanisms vary: drought, disease, invasion. But often there is a common thread. A civilization becomes dependent on a particular resource or system. That system fails. And lacking alternatives, the civilization collapses. Our resource is electricity. Our system is the technological infrastructure that generates and distributes it. What happens when that system fails globally and simultaneously? Some people hear these scenarios and assume we would adapt. Humans are resilient. We would figure it out. And to an extent, that is true. People would organize locally. Communities would share resources. Skills like farming, water purification, basic medicine would become invaluable again. But there is a dark side to that adaptation. 7.8 billion people live on Earth. The majority live in cities. Those cities import food, import water, import energy. If those imports stop, the carrying capacity of urban environments drops to nearly zero. Where do those people go? What do they eat? How do they survive? Throughout history, famine and resource scarcity have driven migration, conflict, and death on massive scales. We like to think we are beyond that now. We have technology, we have logistics, we have global coordination. But all of that is built on electricity. Remove electricity, and we are not so different from any other civilization facing existential resource constraints. Now consider timing. The scenarios described above assume a solar storm hits during average conditions. But what if it hits during winter in the northern hemisphere? What if it hits during a heat wave? What if it hits during a pandemic, when medical systems are already strained? The May 2024 storm was strong, but it occurred in spring with generally favourable weather. If the same storm had struck in January with temperatures below freezing across much of North America and Europe, the death toll from hypothermia alone would have been catastrophic. Or consider geopolitics. A Carrington-level storm would not hit just one country, it would hit everyone. But the impacts would be uneven. Countries with older, less resilient grids would suffer more. Countries with robust disaster preparation and distributed generation would fare better. In the chaos, would nations cooperate or compete? Would they share resources or hoard them? Would the breakdown of global communications prevent coordination, leaving each nation to fend for itself? There is a concept in systems theory called brittleness. A brittle system is one that appears robust under normal conditions, but fails catastrophically when stressed beyond a critical threshold. Modern civilization is brittle. We've optimized for efficiency, for just-in-time delivery, for interconnected networks that maximize productivity. But efficiency is the enemy of resilience. The same globalization that allows us to manufacture goods cheaply on one continent and consume them on another also means that disruptions anywhere propagate everywhere. A solar storm is not an enemy that can be negotiated with or deterred. It is a force of nature, as inevitable as earthquakes or volcanic eruptions. The question is not if another Carrington-level event will occur. The question is when, and whether we will be ready. Some experts estimate Carrington-level storms happen every 100 to 150 years. The last one was 1859. That puts us statistically in the window. Others suggest the frequency might be higher. A 2012 study examining tree ring data and ice cores found evidence of massive solar storms throughout history, events that left no written record because they occurred before or during pre-industrial eras. These storms, measured by radioactive isotopes deposited in tree rings, indicate that Carrington-level events might happen more often than we thought. In July 2012, a massive CME erupted from the Sun and raced through Earth's orbit. Had it occurred 1 week earlier, it would have struck us directly. Scientists who analysed the data concluded it was comparable in intensity to the Carrington event. We missed it by 9 days. 9 days of Earth's orbital motion around the Sun. That is how close we came. The Sun does not care about our schedules. It does not care about our infrastructure or our economies or our politics. It is a massive fusion reactor, converting hydrogen to helium, releasing more energy every second than humanity has produced in its entire history. And sometimes, through mechanisms we still do not fully understand, it hurls a fraction of that energy toward us. We live in a cosmic shooting gallery, and we have built a civilization made of glass. Every solar cycle, the risk increases. Every new sunspot, every X-class flare, every halo CME is a reminder that our technology, for all its wonders, is vulnerable. The storm that just passed was a warning, a preview, a test of systems that thankfully largely held. But the next storm might be stronger. The next one might hit when we are less prepared. The next one might be the extreme event that scientists warn about, the one that pushes our brittle civilization past its breaking point. And the truly unsettling part? We would have about 30 minutes of warning before it hit. Ground-level radiation event, the silent threat nobody saw coming neutron monitors, are not the kind of equipment that makes headlines. They sit quietly in research facilities around the world, measuring cosmic ray flux, contributing data to long-term studies of solar activity and galactic radiation. Most people have never heard of them, but on November 11th, 2025, at 10:04 UTC, neutron monitors from the Arctic to the equator registered something that made veteran space physicists check their instruments and call colleagues. The count rates were spiking, sharply, simultaneously, globally. A ground-level event was underway, and it was significant. To understand why this matters, you need to understand what normally protects us from space radiation. Earth sits in a cocoon of magnetic field, generated by the churning metallic core thousands of miles below our feet. This magnetosphere extends tens of thousands of miles into space, deflecting the solar wind, channeling charged particles toward the poles, creating a protective bubble that shields the surface from the worst of what the cosmos throws at us. It is why life exists here. It is why we do not need radiation suits to walk outside. But the magnetosphere is not perfect. High-energy particles, particularly protons accelerated to relativistic speeds during solar flares, can sometimes penetrate it. Most of the time, they are stopped by the atmosphere itself. Air is matter, and matter absorbs radiation. The higher the energy of the particle, the deeper it penetrates before being absorbed. During a ground-level event, the energies are so extreme that particles make it all the way through. This is what happened during the X5.1 flare. Professor Clive Dyer of the Surrey Space Centre called it very significant. The particles were powerful enough to reach the ground, not in quantities that pose immediate health risks to people on the surface. The atmosphere still provides enormous shielding, but powerful enough that we could measure them. Powerful enough that, at high altitudes and high latitudes, radiation exposure becomes a concern. Airlines operating polar routes received warnings. Flights between North America and Asia, flights between Europe and North America, routes that traverse the Arctic to save time and fuel, these all pass through regions where Earth's magnetic field provides less protection. The atmosphere is thinner at cruising altitude. Flight crew and passengers on these routes receive higher radiation doses than people on the ground. During normal conditions, this is not a problem. The doses are low, comparable to a chest X-ray over the course of a few flights. But during a ground-level event, the doses increase, significantly. Aviation regulators have dose limits for crew members. If those limits are approached or exceeded, flights must be rerouted or delayed. During the November 11th event, some airlines diverted polar routes to lower latitudes, adding flight time and fuel costs but reducing radiation exposure. This is standard protocol, implemented based on real-time data from space weather monitoring systems, but it raises an uncomfortable question. If a ground-level event from a single X-class flare requires rerouting flights, what happens during a much more intense storm? Astronauts on the International Space Station move to better shielded areas. The ISS orbits at roughly 400 kilometers altitude, well within the magnetosphere but above most of the atmosphere. During solar radiation storms, particularly those with ground-level components, astronauts are exposed to significantly elevated radiation levels. The station has areas with additional shielding, typically near the center of the habitable modules, surrounded by equipment and supplies that provide some protection. During high radiation events, astronauts shelter there, limiting their time in more exposed areas and postponing any planned spacewalks. Spacewalks during solar radiation storms are exceptionally dangerous. Outside the hull of the station, you have only your suit between you and the radiation. Spacesuits provide some shielding, but not much. An astronaut caught outside during a major solar proton event could receive a dose high enough to cause acute radiation sickness, high enough to be fatal. This is not theoretical. Mission planners monitor space weather constantly, and extravehicular activities are scheduled around solar activity forecasts. When flares erupt, when proton storms begin, astronauts stay inside. But space stations are not the only concern. Satellites throughout low Earth orbit were bombarded. These spacecraft have radiation shielding, but it is minimal. Mass is expensive to launch, so designers minimize it wherever possible. Electronics are hardened against radiation through careful component selection and redundancy, but there are limits. High-energy protons can penetrate spacecraft walls and interact with computer memory, causing single-event upsets. A bit flips from 0 to 1 or 1 to 0. In most cases, error correction algorithms catch this and fix it. But sometimes the bit that flips is critical. Sometimes it causes a system crash, a loss of pointing control, a permanent malfunction. The February 2022 Starlink loss was attributed to atmospheric drag during a relatively modest geomagnetic storm. But satellites are also vulnerable to direct radiation damage. Solar panels degrade over time as high-energy particles damage the semiconductor materials that convert sunlight to electricity. Normally this degradation is gradual, factored into mission planning. But during intense solar proton events, years of degradation can occur in hours. Electronics can suffer cumulative damage, latent faults that do not cause immediate failure but reduce operational lifespan. How many satellites were affected by the November 11th ground-level event? We will not know for months. Operators do not always disclose when spacecraft experience anomalies, but history provides clues. During the Halloween storms of October 2003, dozens of satellites reported problems. Some lost attitude control, some had memory errors, some simply went dark and never recovered. The radiation environment during those storms was extreme, and the impacts were widespread. There are over 7,000 active satellites in orbit today. Most are in low Earth orbit, where radiation exposure is highest. During solar cycle 25, which is proving more active than predicted, these satellites will face an increasingly hostile radiation environment. Each major flare, each ground-level event chips away at their operational margins. Eventually, critical systems fail, and with tens of thousands more satellites planned for launch in the coming years, the vulnerability only increases. Now consider what a ground-level event means for people on the ground. Not immediate danger. The atmosphere is too effective a shield for that. But chronic exposure is a different story. Airline crew, frequent flyers, people living at high altitudes, all receive elevated radiation doses over their lifetimes. Most of this comes from galactic cosmic rays, high-energy particles from supernovae and other astrophysical sources that constantly rain down on Earth. During solar maximum, this galactic cosmic ray flux actually decreases because the enhanced solar wind provides better shielding. But solar energetic particle events add another source. and during ground-level events the dose rates can spike dramatically. Studies of airline crew have found slightly elevated cancer rates compared to the general population. The increases are small, and there are confounding factors, but radiation exposure is considered a contributing factor. If ground-level events become more frequent, if solar cycle 25 continues to exceed predictions, those dose accumulations increase. For most people, the risk remains negligible, but for those with high occupational exposures, for astronauts planning long-duration missions, for anyone considering living on Mars where there is no magnetosphere and minimal atmosphere, these are not abstract concerns. There is also the question of what we do not fully understand. Radiation biology is complex. We know high doses cause acute effects. We know chronic low doses increase cancer risk. But the mechanisms, the dose rate dependencies, the interactions with other environmental factors, these are areas of ongoing research. Ground-level events provide natural experiments, unwanted but valuable, that help us understand how radiation propagates through the atmosphere and how it might affect biological systems. The November 11th event was significant but not extreme. Neutron monitor count rates increased, but not to the levels seen during historic ground-level events, like the one in January 2005 or the famous event in February 1956, which remains one of the strongest ever recorded. Those events produce count rate increases of thousands of %. The November 11th event was more modest, significant enough to warrant attention, significant enough to trigger aviation warnings, but not catastrophic. Yet even this moderate event revealed vulnerabilities. Airlines had to reroute flights, incurring costs and delays. Astronauts had to shelter, disrupting work schedules. Satellites were exposed to elevated radiation, accumulating damage that shortens lifespans, and all of this from a single X-class flare. What happens when AR4274, which is still active and still Earth-facing, produces another eruption? What happens when the next sunspot region develops an even more unstable magnetic configuration? Space weather forecasters watch the sun constantly. They monitor active regions, track coronal holes, analyze magnetic field data looking for signs of imminent eruptions. When a major flare occurs, they issue alerts within minutes. Solar radiation storm warnings go out to airlines, to space agencies, to satellite operators. But these warnings are reactive. We see the flare, we issue the warning, and then we wait to see what happens. The particles arrive in tens of minutes. The CME arrives in days. But by the time we see the flare, it has already happened. The particles are already on their way. Some particles travel so fast they arrive before the light from the flare. Think about that. The flare produces a flash of X-rays and extreme ultraviolet radiation that travels at light speed and reaches us in 8 minutes. But the most energetic protons, accelerated to 99% of light speed or higher, arrive almost as quickly. By the time we detect the flare, the fastest particles are already hitting us. There is no warning, no time to react, no possibility of taking protective action. This is the reality of ground-level events. They are simultaneous with their detection, and if a truly extreme event occurs, if the sun produces a proton flux orders of magnitude higher than what we just experienced, the consequences could be severe. Satellites could be disabled en masse. Astronauts could receive doses that threaten their lives. Even people on high-altitude polar flights could face exposures that, while not immediately dangerous, significantly increase lifetime cancer risk. We have instruments now that we did not have during the Carrington event. We can measure radiation in real time. We can issue warnings. We can take protective actions. But we cannot prevent the events. We cannot shield the entire planet. We cannot stop high-energy protons from penetrating the magnetosphere and atmosphere. All we can do is monitor, warn, and adapt. The ground-level event on November 11th was a reminder that space weather is not just about pretty auroras and power grid concerns. It is about radiation, about particles moving at relativistic speeds, about an environment that, for all our technological sophistication, we still struggle to predict and protect against. The sun is a nuclear furnace, and sometimes it hurls the products of that fusion directly at us. We exist in its radiation field, shielded by magnetic fields and atmosphere, but not invulnerable. And as we expand into space, as we put more satellites in orbit, as we plan missions to the Moon and Mars, our exposure to these events will only increase. What if the next storm hits? During winter, January 14th, 2026. The scenario planners at FEMA begin their simulation at this date for a reason. Midwinter, northern hemisphere temperatures well below freezing across most of the United States and Europe, home heating systems running at full capacity, power grids strained by peak demand, and then, at 0300 UTC, the sun erupts with an X9 flare followed by a massive, fast-moving CME that reaches Earth in under 18 hours. The simulation is called Dark Winter. It has been run multiple times, each iteration revealing new vulnerabilities, new cascading failures, new ways in which a solar storm during peak winter conditions could transform from disaster to catastrophe. The results are classified, not because they reveal military secrets, but because they are so disturbing that releasing them publicly might cause panic. But elements of the simulation have leaked. Academic researchers have published similar studies, and piecing together the available information paints a picture of what happens when the power goes out in January and does not come back on. Hour 1. The CME strikes Earth's magnetosphere. Geomagnetically induced currents surge through power transmission lines. Transformers across the northern United States and Canada begin to fail. Operators attempt to implement emergency protocols, shedding load, isolating vulnerable equipment, but the intensity of the storm overwhelms their efforts. Within 60 minutes, major sections of the grid are offline. 40 million people lose power, not just lights, not just appliances, heat. Hour 6. Outside temperatures in Minneapolis are -15 Fahrenheit. Inside temperatures in houses without power are dropping rapidly. Modern homes are well insulated, which helps for a while, but without active heating, they equilibrate with outside conditions over the course of hours. People bundle up, gather in single rooms, try to stay warm. Some have fireplaces or wood stoves, most do not. Natural gas heating systems require electricity to run blowers and control systems. They do not work without power. Hour 12. Hospitals are operating on emergency generators. These systems are designed to keep critical equipment running, not to heat entire buildings. Staff begin moving patients to smaller areas that can be warmed. Elderly patients, infants, anyone with compromised health. These populations are particularly vulnerable to cold. Hypothermia sets in when core body temperature drops below 95 Fahrenheit. Severe hypothermia, where core temperature falls below 82, is often fatal. Hour 24. One full day without power. Water pipes in unheated buildings begin to freeze and burst. Once water pipes freeze, they are not just blocked. The ice expands, cracking the pipes. When power eventually returns and the ice melts, those buildings will flood. But flooding is a future problem. The immediate problem is that people are dying. Carbon monoxide poisoning cases surge. Desperate to stay warm, people burn charcoal indoors, run gasoline generators in garages or basements, use camping stoves without adequate ventilation. Carbon monoxide is odorless, colourless, and deadly. It binds to hemoglobin more readily than oxygen, causing hypoxia. Victims feel tired, confused, then lose consciousness. Without medical intervention, they die. During power outages, emergency rooms see waves of CO poisoning cases, but during dark winter, emergency rooms are overwhelmed, running on generators, struggling to maintain operations. Day 3. Food supplies in cities are running low. Grocery stores were emptied within hours of the power failure. Even if there was food in warehouses, distribution has collapsed. Trucks cannot refuel. Traffic signals are dark, making urban driving chaotic. Some roads are blocked by accidents, and even if trucks could reach stores, the stores have no way to conduct transactions without power. Money in a powerless world becomes meaningless. People are breaking into stores, into homes, looking for food, for warmth, for anything that might help them survive. Police, also without power and heat, struggle to maintain order. Some jurisdictions declare martial law, others simply collapse into chaos. In rural areas, neighbours help neighbours. In cities, anonymity and desperation create violence. Day 7, 1 week. The official estimate, never publicly confirmed but leaked by multiple sources, is that death toll by this point would exceed 100,000 in the United States alone. Most from hypothermia, many from carbon monoxide poisoning, some from violence, some from medical conditions that would have been treatable with electricity. People on dialysis, people dependent on oxygen concentrators, people with pacemakers whose batteries died, infant mortality spikes. And still, the power is not restored, because the transformers that failed are not easily replaced. Emergency crews are working to repair what can be repaired, but the scale of the damage exceeds available resources, and the crews themselves are affected. They are cold, their families are cold. The pressure to restore power is immense, but the technical challenges are overwhelming. Day 14, 2 weeks. If any region has restored power, it is only in limited areas. Most of the grid remains dark. By now, essentially, everyone in affected areas has either found a heated shelter, typically a government facility with generators, or they have left, attempting to migrate to areas with power. Roads out of blacked out regions are clogged with vehicles that ran out of fuel and were abandoned. Refugees stream south toward warmer climates, toward regions that still have power. But those regions are not prepared for millions of displaced people. Shelters overflow, resources strain, and the social fabric begins to tear. There are not enough facilities, not enough food, not enough medicine to handle this kind of mass displacement. Fights break out. Disease spreads. Flu, normally a manageable winter illness, becomes deadly in crowded, unsanitary conditions. Day 30. 1 month. Official estimates, which again are not public, suggest the death toll could reach 500,000 to 1 million in the United States alone. The economic cost is incalculable, not because economists cannot estimate it, but because the economy, as we understand it, has ceased to function. Businesses are closed, supply chains are destroyed, financial systems are offline. The question is not how much damage has been done, but whether recovery is even possible. This is not a zombie apocalypse. This is not a nuclear war. This is a solar storm hitting during winter, a natural event driven by well-understood physics, causing a power outage that lasts weeks instead of hours, and the human toll is catastrophic. Now consider that the scenario above assumes only the northern United States and Canada are affected, but a major solar storm would hit the entire planet simultaneously. The northern hemisphere in winter, the southern hemisphere in summer, Europe in winter, Asia in winter. Different continents would face different challenges, but all would be struggling simultaneously. There would be no unaffected region to send aid, no untouched economy to provide resources. Every nation would be in crisis mode. Europe, with its older grid infrastructure and higher population density, might face even worse outcomes. Asian megacities, home to tens of millions, could see death tolls that dwarf Western estimates. And less developed regions, which often have less robust power infrastructure to begin with, might actually fare better simply because they are less dependent on electricity for survival. Rural agricultural communities which can heat with wood and have local food sources would be more resilient than urban populations. The psychological impacts are harder to quantify but no less real. Modern humans, particularly in developed nations, have never experienced sustained deprivation on this scale. We have no living memory of what it means to be cold and hungry, and unable to do anything about it. The trauma would be generational, and the social changes that emerge from that trauma could reshape civilization in unpredictable ways. Some disaster researchers argue that major crises bring communities together, that humans are fundamentally cooperative and will help one another in times of need. The evidence for this is mixed. After Hurricane Katrina, There were both stories of incredible altruism and stories of violence and exploitation. After the 2011 Fukushima disaster, Japanese society demonstrated remarkable resilience and cooperation. But Japan is a culturally homogeneous nation with strong social cohesion. Would the United States, with its deep political divisions and widespread gun ownership, respond similarly? There is also the question of government response. Emergency management systems are designed for localized disasters. Hurricanes affect regions, earthquakes affect areas, but solar storms affect continents. FEMA, designed to coordinate responses to events where surrounding regions can provide aid, would be faced with a scenario where every region is simultaneously affected. The National Guard, called up to maintain order and distribute supplies, would be operating in the same cold, powerless environment as everyone else. And what about nuclear power plants? These facilities require constant cooling. They have backup generators, and those generators have fuel for days or weeks. But if the power outage extends beyond that, if refueling cannot occur because transportation infrastructure has collapsed, reactors must be shut down. The shutdown process is complex and requires external power. Without it, you risk meltdowns. Fukushima happened because tsunami damage prevented cooling. A widespread prolonged blackout could create multiple Fukushimas simultaneously. Military readiness collapses. Defense systems require power. Communications require power. Even if bases have generators, those generators require fuel. In a prolonged blackout, military forces become focused on survival and domestic stability, not external threats. If adversarial nations are less affected, or if they recover more quickly, the geopolitical implications are staggering. Dark winter is not the only scenario that has been modelled. There are simulations for solar storms during summer heat waves, where lack of air conditioning causes heatstroke deaths. There are simulations for storms during pandemics, where medical systems already at capacity simply collapse. There are simulations for storms during harvest season, where loss of power means crops rot in silos and the following year faces famine. Every scenario reveals the same fundamental truth. We have built a civilization that requires electricity to function, not desires it, requires it. And we have built that civilization in an environment where electricity can be taken away by forces entirely beyond our control. The sun does not care about our needs. It does not care about optimal timing. It will produce another major storm whenever the physics dictates, and we will have to deal with the consequences. The question is whether we will prepare, whether we will harden the grid, install protective equipment, train response teams, educate the public, or whether we will continue as we are, hoping that the next big storm does not come during winter, does not come when we are vulnerable, does not push us past the breaking point. Because if it does come during winter, if it hits when temperatures are below zero and power grids are strained and millions of people depend on electricity for heat, the scenario planners believe we could see death tolls that rival major wars, not from violence, not from disease, from cold, from the simple, brutal fact that humans cannot survive extended exposure to freezing temperatures without external heat sources. The storm that just passed was in November, autumn, mild weather, no heating crisis. We were lucky. Next time, we might not be. Sunspot AR4274, the monster that won't stop. There are roughly 1,000 distinct sunspot regions observed during each 11-year solar cycle. Most last a few days. Some persist for weeks. A handful become legendary, etched into solar physics history books as particularly active, particularly large, or particularly productive of major flares. Region 3664, which produced the May 2024 superstorm, earned that status. Region 3842, which fired off the X9 flare in October 2024, joined the list. Now we can add AR4274. As of today, November 12th, 2025, this region remains visible on Earth-facing solar disk. Its magnetic configuration, classified as beta-gamma delta, indicates complexity that breeds instability. The classification system describes how magnetic polarities are arranged. Beta means there is both positive and negative polarity present. Gamma means they are irregularly distributed, tangled. Delta means opposite polarities are pushed so close together that they share a single penumbra, the lighter area surrounding the dark umbra of a sunspot. This is the configuration that produces the most energetic flares. AR4274 has maintained this delta configuration for days, not hours. Days, and it has been producing. November 9th, X1.7, November 10th, X1.2, November 11th, X5.1, the strongest flare of 2025. 3 X-class eruptions in 3 days, from the same region. This is rare. Not unprecedented, but rare. Most sunspot regions produce no X-class flares during their entire visible disk transit. Some produce 1, very few produce multiple, and AR4274 is not finished. NOAA forecasters, analysing the region's magnetic field measurements and historical behaviour, estimate an 80% probability of additional M-class flares in the next 48 hours. M-class is still significant. The May 2022 Starlink loss was caused by events around an M-class flare, but more concerning is the 55% probability of another X-class eruption. 55%, essentially a coin flip. Will AR4274 produce another major flare, or will it decay into quiescence? We do not know. We cannot know. Solar flare prediction is notoriously difficult. We can assess probabilities based on magnetic configuration, but the actual trigger, the moment when magnetic fields reconnect and release their energy, remains unpredictable. What we do know is that the region is still there, still active, still Earth-facing. For the next several days, until solar rotation carries it around the western limb and out of view, every X-ray flux spike, every brightening in extreme ultraviolet, every coronagraph image showing material lifting off the surface will send pulses of adrenaline through space weather forecasting centres worldwide. Amateur astronomers with hydrogen alpha filters have been watching the region obsessively. Images posted online show a massive complex of sunspots, dark blotches against the brilliant solar surface, structures so large that multiple Earth could fit inside them. The umbra, the darkest central region of each spot, appears black in contrast to the surrounding photosphere, though it is still glowing at temperatures of several thousand degrees. The penumbra, with its radial filamentary structure, shows the magnetic field lines channeling plasma outward from the intense field concentration. Professional observatories have trained their instruments on AR4274 continuously. The Solar Dynamics Observatory, in geosynchronous orbit, captures images every few seconds across multiple wavelengths. Watching these time-lapse sequences, you can see the region evolving, plasma loops tracing magnetic field lines rise and fall, bright points, indicative of magnetic reconnection, flare briefly. The region is alive with activity, and any of that activity could trigger the next major eruption. There is also the question of what happens when AR4274 rotates to the far side of the Sun. We will lose direct visual observation. Helioseismic imaging can detect large active regions on the far side by measuring acoustic waves travelling through the solar interior, but the resolution is limited. If the region produces a major flare while hidden, we might not know until its effects arrive at Earth. CMEs from the far side do not usually hit us, but solar energetic particle events can wrap around the Sun's magnetic field structure and reach us even from non-Earth-facing eruptions. And if AR4274 remains active for another 2 weeks, it will rotate back into view. We will get a second disk transit. More opportunities for Earth-directed eruptions. More days of elevated risk. This is one of the challenges of living with an active sun. Sunspot regions are not isolated events. They persist, they evolve, they return, and during solar maximum, when multiple active regions can be present simultaneously, the cumulative risk becomes substantial. You're not just watching one region, you're watching 5, 10, sometimes 20 regions, each with its own magnetic configuration, its own flare potential, its own ability to produce Earth-directed CMEs. AR4274 has become the focus because of what it has already done. 3 X-class flares, including the strongest of the year. Multiple CMEs, one of which merged into a cannibal storm. Ground-level radiation event. G4 geomagnetic storm. This region has, in less than a week, demonstrated the full range of solar activity impacts, but it is not alone. Region 4275, just to its west, is also classified as Beta-Gamma-Delta, smaller, less active so far, but possessing the magnetic complexity to produce major flares. And new regions continue to emerge as the Sun rotates, fresh magnetic flux rising from below the photosphere, forming new sunspots, new potential threats. Solar Cycle 25 has exceeded predictions. When the Solar Cycle 25 prediction panel released their forecast in December 2019, they anticipated a cycle similar to the relatively weak Solar Cycle 24. Smooth sunspot number, maximum of 115, occurring around July 2025. But observations from 2020 onward showed significantly more activity than predicted. By 2022, there had not been a single spotless day since the cycle began. By 2024, monthly average sunspot numbers were consistently exceeding predictions. The Sun, it seems, did not read the forecast. Why Solar Cycle 25 is stronger than expected remains a topic of research. Solar cycle prediction is part science, part art, with methods ranging from statistical extrapolation to complex dynamo models. But the Sun is a chaotic system, and chaos is inherently unpredictable. Small differences in initial conditions, in magnetic field seed strengths, in meridional flow velocities can produce large differences in outcomes. What we can say is that we are likely at or near solar maximum now, the peak of the cycle, the period when flare activity is highest, when the most sunspot regions are present, when the probability of major storms is greatest, and based on historical patterns, this peak will last not weeks but months, possibly into late 2026. We are in the danger zone. Every solar cycle has its memorable events. Solar Cycle 19, which peaked in 1958, produced the second largest geomagnetic storm of the modern era. Solar Cycle 21 gave us the 1989 Quebec blackout. Solar Cycle 23 produced the Halloween storms of 2003. Solar Cycle 24, despite being weak overall, produced the July 2012 near miss. And Solar Cycle 25 has already given us multiple major storms, with the May 2024 event and now the November event marking this cycle as particularly consequential. The question is whether the worst is yet to come, whether AR4274 will produce an even larger flare, whether a new region will develop with even more extreme magnetic complexity, whether the next major CME will be faster, more massive, better aligned with Earth's magnetic field than anything we have seen so far. Some solar physicists argue that we have been relatively lucky. The May event, while strong, did not cause widespread transformer failures. The November event, despite reaching G4, did not create prolonged blackouts. The X9 flare from October 2024 occurred when the region was near the solar limb, and the CME mostly missed Earth. We have had warnings, demonstrations of what the Sun can do, without experiencing the worst-case scenario. But luck, by definition, runs out. There is a concept in risk management called normalcy bias, the tendency to assume that because something has not happened recently, it will not happen in the future. We see this in many contexts. People living near dormant volcanoes, assuming they will remain dormant. People in earthquake zones, assuming the next big one will not come in their lifetime. And people living in a technologically advanced civilization, assuming the Sun will not produce a storm that brings it all crashing down. But the Sun does not care about our assumptions. AR4274 is still there, still active, still capable of producing major flares, and behind it, rotating into view, new regions will emerge. The magnetic field below the photosphere continues to churn, continues to generate new flux, new sunspots, new opportunities for eruption. Space weather forecasters watch. They issue predictions, probabilities, warnings, but they cannot stop the events. They cannot calm the sun. All they can do is observe, model, and hope that when the next major eruption occurs, it happens when Earth is not in the firing line, that the CME is slower, that its magnetic field is aligned northward instead of southward, that some combination of factors reduces its impact. AR4274 will eventually decay. The magnetic fields will diffuse, the sunspots will fragment and disappear, and the region will become a footnote in solar cycle statistics. But right now, in mid-November 2025, it remains one of the most active regions of this solar cycle. Monster that produced 3 X-class flares in 3 days, a region that sent a cannibal CME racing toward Earth, a threat that has not finished its performance. And somewhere on the far side of the sun, in regions we cannot yet see, new sunspots are emerging, new magnetic complexity is developing, new potential monsters are being born. Because solar maximum is not a moment, it is a period, and we are in the middle of it. What if all satellites go dark simultaneously? There are approximately 7,000 active satellites orbiting Earth right now. This number has exploded in recent years, driven primarily by mega constellations like Starlink, OneWeb, and others planning to provide global internet coverage. These satellites occupy various orbits. Low Earth orbit, between 160 and 2,000 kilometers altitude. Medium Earth orbit, around 20,000 kilometers where GPS satellites reside. Geostationary orbit, at 35,786 kilometers, where communications satellites hover for fixed points on Earth. Each orbit has its own radiation environment, its own vulnerabilities, but all of them, every single satellite currently operating, shares one critical weakness. They were designed during a period of relatively low solar activity, and now solar activity is high and climbing. The European Space Agency ran a simulation in mid-2025. They called it Carrington Event Response Exercise. The scenario was straightforward. A Carrington-level solar storm strikes. X-45 class flare, multiple massive CMEs, ground-level events orders of magnitude stronger than anything in modern history. How do satellites respond? The answer, according to the simulation results, is that they do not. They die, almost all of them. Jorge Amaya, ESA's space weather modelling coordinator, stated it plainly. The immense flow of energy ejected by the sun may cause damage to all our satellites in orbit. Satellites in low Earth orbit are typically better protected by our atmosphere and our magnetic field from space hazards, but an explosion of the magnitude of the Carrington event would leave no spacecraft safe. No spacecraft safe. Think about what that means. GPS navigation goes dark, satellite communications vanish, weather satellites stop transmitting data, Earth observation satellites cease operations, military reconnaissance fails, scientific missions end. The International Space Station, if it survives at all, loses contact with ground control. Astronauts are on their own. The mechanisms of failure are multiple and cumulative. Start with the radiation. During a major solar storm, the flux of energetic protons increases by factors of thousands or millions compared to quiet conditions. These particles penetrate spacecraft walls, interact with electronics, cause single event upsets in computer memory, damage solar cells, degrade sensors. Most satellites have some radiation tolerance, but there are limits. When particle energies exceed shielding capabilities, when dose rates exceed what error correction can handle, systems fail. Then there is atmospheric expansion. During geomagnetic storms, energy pours into the upper atmosphere. The thermosphere, normally cold and tenuous, heats up and expands. At low Earth orbit altitudes, this means increased air density. Air density means drag. Drag means orbital decay. Satellites must fire thrusters or use magnetic torquers to maintain altitude. But in a Carrington-level storm, the expansion is so extreme that some satellites cannot compensate. They begin a death spiral, descending into denser layers, heating up from atmospheric friction, eventually burning up on re-entry. This is what happened to 38 Starlink satellites in February 2022. A relatively modest geomagnetic storm caused atmospheric expansion at their deployment altitude of 210 kilometers. SpaceX tried to command the satellites into safe mode, orienting them edge on to minimize drag, but the density was too high. The satellites could not fight it. One by one, they fell. February 2022 was a G1 storm, minor on the NOAA scale. A Carrington-level event would be G5, possibly beyond the scale entirely. If a G1 storm can destroy nearly 40 satellites at 210 kilometers, what does a G5 storm do to the thousands of satellites between 300 and 600 kilometers? GPS satellites, in medium Earth orbit, face different challenges. They are above the worst of the atmospheric effects, but they are deeper in the radiation belts. During solar storms, these belts intensify and shift. Satellites designed to operate in a certain radiation environment suddenly find themselves in a much harsher one. Electronics fail. Solar panels degrade catastrophically. Gyroscopes and star trackers, needed for attitude control, are blinded by radiation-induced noise, and if GPS goes down, the cascading effects are staggering. GPS is not just for navigation. It provides timing signals used for telecommunication synchronization, financial transaction timestamps, power grid coordination, emergency services dispatch. When GPS satellites fail, the systems that depend on them fail. Cell phone networks lose synchronization and drop calls. ATMs cannot process transactions. Traffic lights go haywire. Emergency services cannot locate callers. And airline navigation, which relies on GPS for precision approaches and en route guidance, reverts to older, less accurate methods. Geostationary satellites, those massive communications birds that broadcast television and provide backbone internet connectivity, are in perhaps the worst position. At 35,000 kilometers, they sit in the heart of the outer radiation belt. They're huge, expensive, and not easily replaced. Each one costs hundreds of millions of dollars and takes years to build. If a Carrington-level storm damages or destroys multiple geostationary satellites simultaneously, replacing them would take years, perhaps a decade. During that time, global communications would be crippled. Intercontinental phone calls would become difficult or impossible. International broadcasting would collapse. Maritime and aviation communications, which rely heavily on geostationary satellites, would fail. Remote regions served only by satellite internet would go dark, and in a post-storm world, when you desperately need communications to coordinate recovery efforts, you would not have them. The simulation revealed something else disturbing. Even satellites that survive the initial radiation storm face long-term degradation. Solar panels lose efficiency. Batteries suffer capacity loss. Electronics develop latent faults that cause failures months or years later. A satellite with a 10-year design life might last 5. A satellite with 5 years might last 2. The entire orbital infrastructure ages rapidly, compressed by the harsh radiation environment, and begins failing en masse. There is also the debris problem. When satellites fail and lose attitude control, they start tumbling. Tumbling satellites are harder to track, harder to avoid, and if their orbits decay enough, they can collide with operational satellites. Each collision creates more debris. More debris creates more collision risk. This is the Kessler syndrome, a cascade where orbital debris becomes so dense that space becomes unusable. A Carrington-level storm would not directly trigger Kessler syndrome, but it would create conditions that make it more likely. hundreds or thousands of satellites failing simultaneously, orbital debris increasing, tracking networks which depend on ground-based radars and telescopes, potentially offline due to power grid failures, satellite operators unable to coordinate avoidance maneuvers because communications are down. The probability of cascading collisions would increase dramatically. Some engineers argue that modern satellites are more resilient than older ones. They have better radiation shielding, more robust error correction, redundant systems. This is true. But resilience is relative. A satellite designed to survive a 10-year mission in the current radiation environment may not survive a week in a Carrington-level environment. The dose rates, the particle energies, the sustained bombardment all exceed design parameters. And then there is the question of replacement. The global satellite manufacturing capacity is finite. A few dozen satellites per year from major manufacturers. Mega constellation operators like SpaceX can produce more, but even they are limited by manufacturing throughput. If you lose hundreds or thousands of satellites simultaneously, replacing them takes years. And during those years, you operate with degraded or absent satellite services. Consider what that means for weather forecasting. Meteorology relies on satellite data. Without geostationary satellites, providing constant imaging, without polar orbiting satellites measuring temperature and humidity profiles, forecast accuracy plummets. You might still predict major storms a day or two out, but the 5 to 7 day forecasts become unreliable. Hurricanes could develop with less warning. Tornado outbreaks could surprise communities. Winter storms could paralyze regions before adequate preparation. Consider military implications. Modern warfare is satellite dependent. Communications, reconnaissance, navigation, precision-guided weapons. If those satellites go dark, military capabilities revert to pre-digital age levels. Some nations, recognizing this vulnerability, have maintained or developed non-satellite capabilities specifically for this scenario. Others have not. The strategic balance shifts dramatically. Consider financial systems. High-frequency trading relies on microsecond timing precision, provided by GPS. When GPS fails, trading becomes impossible or fraught with errors. Stock exchanges might shut down to prevent chaos. And in a world already reeling from power outages and supply chain collapse, financial panic would compound every other problem. But perhaps the most disturbing aspect is how unprepared we are. Space agencies run simulations, satellite operators have contingency plans, but the scale of a simultaneous loss of most orbital assets has never been experienced. We do not really know what would happen. We do not know if critical government satellites, supposedly more hardened, would actually survive. We do not know if launch capabilities, which require extensive ground infrastructure, would be functional post-storm. We do not know if we could rebuild the orbital infrastructure before societal collapse makes it impossible. Some researchers propose solutions: harden satellites with better shielding, increase redundancy, maintain ground-based backup systems, design satellites that can go into protective hibernation during storms, launch replacement satellites on standby, ready to activate when primaries fail. These are good ideas, but they cost money, add mass, reduce profitability. And in a competitive commercial space industry, companies optimize for normal operations, not extreme events. There is also the argument that a Carrington-level storm is so rare that preparing for it is not cost-effective. After all, if such events only happen every century or two, why spend billions hardening infrastructure against them? This is the same argument that was made about pandemic preparation, and we saw how that worked out. The simulation conducted by ESA, by NASA, by various national space agencies, consistently reaches the same conclusion. A Carrington-level solar storm would devastate orbital infrastructure. Not damage it, devastate it. The key question is not whether it would happen, but when. And whether, when it does, we will have the resources and capability to rebuild in a world where power grids are down, Supply chains are shattered, and international cooperation may be impossible. Gustavo Baldo Carvalho, who led the Sentinel satellite simulations, put it succinctly. The key takeaway is that it is not a question of if this will happen, but when. And his colleague Jorge Amaya added that simulating impacts is similar to predicting effects of a pandemic. We will feel its real effect on our society only after the event, but we must be ready and have plans in place to react in a moment's notice. Right now, we do not have those plans. Not really. We have some contingencies for individual satellite failures. We have some protocols for solar radiation storms. But a scenario where most satellites fail simultaneously, that planning is nascent at best. And when the next Carrington-level storm hits, when 7,000 points of light in the sky go dark, when GPS stops working and communications fail, and weather data vanishes, we will discover just how dependent we have become on an infrastructure we cannot adequately protect. The 30-minute warning system that might save civilization, 1 million miles from Earth, in a gravitationally stable point where the sun's pull balances Earth's, a satellite hangs in space. DSCOVR, Deep Space Climate Observatory. Launched in 2015, it replaced the aging Advanced Composition Explorer, which had been providing solar wind data since 1997. DSCOVR sits at the L1 Lagrange point, directly between Earth and the Sun, in the path of the solar wind, monitoring the stream of particles flowing outward from our star. This satellite is humanity's early warning system. When a coronal mass ejection erupts from the Sun and races toward Earth, we see it in coronagraph images within hours. We can model its trajectory, estimate its speed, predict roughly when it will arrive. But those predictions have uncertainties measured in plus or minus 12 hours. You know a storm is coming, but you do not know exactly when, and you do not know exactly how strong it will be, until it reaches DSCOVR. When the leading edge of a CME passes the satellite, instruments measure its properties directly. Particle density, velocity, temperature, and most critically, the interplanetary magnetic field strength and orientation. That last measurement, the IMF-BZ's component, determines whether the CME will couple effectively with Earth's magnetosphere. A northward BZ typically produces minimal effects. A southward BZ opens Earth's magnetic field, allows solar wind entry, drives geomagnetic storms. From DSCOVR to Earth is approximately 1 million miles. Lightspeed travel time is about 5 seconds, but the solar wind, even during a CME, moves much slower, typically 400 to 800 kilometers per second. Fast by human standards, glacial by cosmic standards. At those speeds, the travel time from L1 to Earth is 30 to 60 minutes. 30 minutes, half an hour. The time it takes to watch a television show, to cook dinner, to commute home from work. That is how much warning we get when a CME is about to strike, and in those 30 minutes critical decisions must be made. The Space Weather Prediction Center operates around the clock. When DSCOVR data shows a significant CME arrival, forecasters issue alerts within minutes. These go to power grid operators, satellite controllers, airlines, government agencies, anyone who needs to know. The alerts specify expected storm intensity, duration, affected regions, and then the clock starts. Power grid operators have protocols. When a major storm warning comes in, they begin shedding load. Non-essential systems go offline first. Industrial users with interruptible contracts get notified. Large transformers, particularly those vulnerable to geomagnetically induced currents, are monitored closely or taken offline temporarily. The goal is to reduce the stress on the system before the storm hits, creating margin for when GICs start flowing. This is what Transpower did in New Zealand during the May 2024 storm. They reduced grid load by 30 to 40% in the hours before impact. When the CME struck and GICs surged, the transformers handled it. Barely, but they handled it. Without that pre-positioning, without that load reduction, some transformers might have failed, and once a transformer fails, you are not bringing it back online quickly. Satellite operators receive the alerts and make their own decisions. Some spacecraft can be put into safe mode, turning off non-essential systems, orienting solar panels edge-on to reduce drag, preparing for elevated radiation. Others, particularly large geostationary platforms, have less flexibility. You cannot move a geosynchronous satellite quickly. You cannot shield it. You just hope the redundancy built into critical systems is sufficient. Airlines reroute polar flights. The decision is not automatic, there are trade-offs. Rerouting adds flight time, burns more fuel, costs money. But if the storm is severe enough, if radiation levels are expected to exceed safety limits, the flights get moved to lower latitudes. Passengers, unaware of the drama unfolding, might notice their trans-Pacific flight taking a slightly different route. They do not know that decision was made 30 minutes before a solar storm hit. But 30 minutes is not much time, especially when you consider what needs to happen. Alerts must be issued. They must reach the right people. Those people must make decisions. Those decisions must be implemented. In a perfect world with perfect communication and perfect coordination, 30 minutes is workable. In the real world, with bureaucracy and uncertainty and competing priorities, 30 minutes is terrifyingly short, and it is only 30 minutes if DSCOVA is working, if the satellite is operational, if its instruments are functioning, if data is transmitting back to Earth. DSCOVA is well past its design life. It was built for a 5-year mission. It has been operating for over 10 years. Components fail, backups are exhausted, and there is no replacement currently in orbit. NASA and NOAA recognize this vulnerability. They developed the space weather follow-on Lagrange 1 mission, SYFEVO L1, designed to replace DSOVR with improved instruments, better radiation tolerance, redundant systems. Launch was scheduled for 2024, then it slipped to 2025, then to 2026. As of today, the satellite is still in development, still not launched, while the aging DSCOVR continues its lonely vigil. If DSCOVR fails before SFO-L1 is operational, we lose that 30-minute warning. We go back to relying on modelling and coronagraph imagery, with their 12-hour uncertainties. Power grid operators would have to implement protective measures hours before a storm might arrive, causing unnecessary disruptions and economic costs, or they gamble, hoping the storm is not as bad as predicted, and risk catastrophic transformer failures if they guess wrong. But even 30 minutes assumes we can predict the storm's intensity from DSCOVR data, and that is not always possible. The magnetic field structure inside a CME is complex. It can vary over small spatial scales. DSCOVR measures conditions at one point. Earth's magnetosphere intercepts a cross-section thousands of kilometers wide. If the strongest southward BZ is not where DSCOVR is, if it is offset to one side, the satellite might measure relatively benign conditions while Earth gets hammered. This happened during some past storms. The forecast, based on DSCOVR data, suggested moderate activity. The actual geomagnetic response was severe. The mismatch caused confusion, delayed responses, left grid operators unprepared for what hit them. Since then, forecasting methods have improved. Statistical models incorporate uncertainty. Ensemble forecasts provide ranges rather than single predictions. But the fundamental limitation remains. One measurement point cannot capture the full structure of something as large and complex as a CME. Scientists have proposed solutions. Launch multiple satellites at L1, spread out to sample different regions of the incoming solar wind. This would provide better spatial coverage, reduce the risk of missing important features. But multiple satellites mean multiple costs, and space weather monitoring, while critical, competes for funding with other priorities. There is also interest in improving models, not just predicting when a CME will arrive, but predicting its internal structure, magnetic field orientation, density variations, velocity profiles. This requires understanding the physics of CME evolution how these structures form in the solar corona, how they propagate through the interplanetary medium, how they interact with solar wind. It requires computational power, observational data, and time. Researchers are working on it. Progress is being made, but we are not there yet. Then there is the question of artificial intelligence. Machine learning models trained on decades of solar wind data and geomagnetic responses can identify patterns that humans miss. The Dagger model, developed by a team including NASA, USGS, and Department of Energy researchers, uses deep learning to predict geomagnetic perturbations based on solar wind measurements. Early results are promising. The model can forecast storm intensity and location with better accuracy than traditional methods. Vishal Upendran, lead author of the paper describing Dagger, stated that with this AI, it is now possible to make rapid and accurate global predictions and informed decisions in the event of a solar storm, thereby minimizing or even preventing devastation to modern society. The code is open source. Power grid operators, satellite controllers, telecommunications companies, anyone who needs it can adopt and integrate it into their operations. But AI models are only as good as their training data. They work well for conditions similar to what they have seen before. If a truly extreme storm occurs, something outside the range of historical data, the models might fail, they might extrapolate incorrectly, they might provide confident predictions that turn out to be wildly wrong. This is a known limitation of machine learning. Interpolation is reliable, extrapolation is risky. Still, improved forecasting is better than nothing, and 30 minutes is better than no warning at all. During the Carrington event in 1859, there was no DSCOV, no satellite network, no space weather prediction center. When the CME hit, it hit without warning. Telegraph operators first knew something was wrong when their equipment started sparking. Today, we would have half an hour to prepare, to brace, to hope that the systems we have built can withstand what is coming. The challenge is ensuring that warning time is used effectively, that alerts reach the right people, that those people take them seriously, that they have plans in place and can execute them quickly. This requires training, regular drills, a culture of preparedness. In the aviation industry, pilots train for emergencies constantly. Simulators throw every conceivable failure at them, so when real emergencies occur, responses are automatic. Space weather preparedness needs the same approach. Grid operators should train on storm scenarios. Satellite operators should rehearse safe mode procedures. Government agencies should conduct exercises simulating the chaos of a major space weather event. Some of this happens. FEMA has run dark winter scenarios. ESA conducted their Carrington simulation. Power companies participate in drills, but it is not universal. Smaller utilities with limited budgets might not prioritize space weather preparedness. Satellite operators, focused on quarterly earnings, might defer expensive hardening measures. And at the government level, with administrations changing and priorities shifting, long-term preparation for rare events often loses out to immediate concerns. The 30-minute warning is a lifeline. It is the thread connecting us to survival during a major solar storm, but it is a fragile thread, dependent on aging satellites, reliant on functioning communication networks, requiring rapid human decision-making in high-stress situations, and ultimately, only valuable if the people receiving the warnings have the tools, the authority, and the will to act. When the next major storm comes, when DSCOVR or its successor detects the leading edge of a massive CME bearing down on Earth, when the IMF-BZ swings southward and forecasters know with certainty that we are about to be hit hard, those 30 minutes will be humanity's last chance to minimize the damage, to power down vulnerable systems, to take satellites offline, to reroute aircraft, to notify hospitals and emergency services, to send out public alerts so people can prepare. 30 minutes. It is not much, but it might be enough. If we use it wisely, if we are prepared, if the systems hold and the warnings work and people respond appropriately, and if we are lucky, very lucky, that 30 minutes of preparation might be the difference between a crisis we recover from and a catastrophe we do not. What if a Carrington-class storm strikes tomorrow, November the 13th, 2025, tomorrow? The simulation starts with a phone call at 0400 UTC. DSCO VR has detected an incoming CME, velocity 2000 km per second, magnetic field strength 65 nanoteslas, BZ component negative 40 nanoteslas and holding steady, travel time from L1 to Earth 25 minutes. This is not a historical scenario. This is not 1859 with telegraph lines and gas lamps. This is tomorrow, with 8 billion people, with cities of 20 million, with power grids connecting entire continents, with 7,000 satellites, with data centers and financial systems and supply chains optimized for efficiency, with everything, absolutely everything dependent on electricity and communications. The alerts go out. Space Weather Prediction Center issues a G5 extreme geomagnetic storm warning. NOAA declares a space weather emergency. The president is briefed. Emergency management activates. Power grid operators across North America, Europe, and Asia receive notifications. This is not a drill. This is the big one. The Carrington event. Today, minute 1. Grid operators begin emergency protocols. But here is the problem. They have 30 minutes total, maybe less. In that time, they need to coordinate across hundreds of utilities, each with their own systems, their own jurisdictions, their own decision-making processes. Some respond immediately, others hesitate, wanting confirmation, wanting to be sure, not wanting to shut down systems unnecessarily. The hesitation costs time. Minute 10. Some major transformers are being taken offline. Load is being shed. But it is not enough. The grid is too complex, too interconnected. You cannot just flip switches and isolate everything. Power flows through the path of least resistance. If you open one path, it redistributes to others. Load balancing is a continuous process, normally managed by automatic systems. But in an emergency, when you're trying to reconfigure the entire grid in 20 minutes, those automatic systems become obstacles. Minute 15. DSCOVA data updates. Magnetic field strength increasing. Now 80 nanoteslas. Velocity holding at 2000 km per second. BZ still strongly southward. Forecasters recalculate. This is worse than Carrington. This is beyond anything in recorded history. Revised estimate. Negative 2000 nanoteslas at peak. Power grid operators, already in emergency mode, realize their protocols are inadequate. This is not a G5 storm. This is a G6, if such a classification existed. Minute 20. Satellite operators have put everything they can into safe mode, but there are limits. Geostationary satellites cannot move. GPS satellites are hardened, but not for this level of radiation. The International Space Station crew have moved to the most shielded module. Astronauts are effectively sheltering in place, 300 kilometers above a planet about to be hit by the storm of the millennium. Minute 25. Commercial airliners, unaware of the drama unfolding, continue their polar routes. Some have been diverted. Others, already mid-flight, cannot reach alternate airports without crossing high-latitude regions. They will be airborne when the storm hits. Pilots will fly through radiation levels that, while not immediately lethal, will deliver doses that significantly increase cancer risk. They have no choice. Minute 30. Impact. The CME slams into Earth's magnetosphere. The leading edge compresses the field from its normal standoff distance of 60,000 kilometers to perhaps 30,000. Energy pours into the system. Currents begin flowing in the ionosphere. Millions of amperes, billions of watts. The aurora oval expands from the poles, spreading toward the equator. Within minutes, Auroras are visible from Singapore, from Cairo, from Rio de Janeiro. The entire night side of the planet glows. On the ground, geomagnetically induced currents surge through power lines. Hundreds of amperes of quasi-DC current flow into transformers. The magnetic cores saturate. Windings overheat. Protective systems designed for normal fault conditions trip. But this is not a normal fault. This is every transformer on the grid experiencing abnormal conditions simultaneously. Protective systems tripping to save individual components crash the entire system. Hour 1. Power grids across North America, Europe and Asia are offline. Not partially, completely. 60% of the world's electricity generation gone in 60 minutes. The remaining 40% in regions less affected by the storm struggle to maintain stability as load redistributes. Some of those grids fail too, unable to handle the sudden changes. Cities go dark, not just lights, traffic signals, water pumps, sewage treatment. Hospitals switch to generators, but generators were designed for temporary outages, for hurricanes or ice storms, for events measured in hours or days, not for an event that will last weeks or months. Hour 3. The radiation storm is at full intensity. Satellites are being bombarded. Single event upsets cascade through systems. Computers reboot, lose data, fail to restart. Solar panels hit by high-energy protons degrade rapidly. Power generation drops. Batteries drain. One by one, satellites go silent. First the small ones in low Earth orbit, then the GPS constellation, finally the massive geostationary platforms. GPS signals disappear. Navigation systems worldwide show error messages. Autonomous vehicles stop functioning. Ships at sea lose positioning. Aircraft navigate by inertial systems and ground-based beacons, where those still work. Financial markets, unable to timestamp transactions without GPS, freeze. Trading halts, banks close. Hour 6. Communications are failing. Cell towers, without power and with satellites down, stop working. Internet backbones, dependent on fiber optic networks that require powered repeaters, go dark. International connectivity, routed through undersea cables and satellite links, collapses. The world fragments into isolated regions, each unable to communicate with the others, each unaware of the full scale of the disaster. Hour 12. In winter regions, people are getting cold. Furnaces do not work without electricity. Some have fireplaces or wood stoves. Most do not. Temperatures inside homes begin to drop. Hypothermia becomes a concern. Emergency services themselves without power and unable to communicate effectively are overwhelmed. In summer regions, the problem is heat. Air conditioning fails. In places like India, the Middle East, the American Southwest, where temperatures exceed human tolerance without cooling, people begin dying. The elderly, the very young, anyone with medical conditions. The death toll starts climbing. Day 1, 24 hours, still no power. The immediate chaos has stabilized into grim survival. People have gathered with neighbors, pooling resources. Communities are organizing, but without communications, coordination is local only. National governments, unable to assess the full situation or communicate with regional authorities, struggle to mount effective responses. Hospitals are in crisis. Generator fuel is running low. Critical patients on ventilators, dialysis, life support. These people have hours to days before their systems shut down. Medical staff, working by flashlight and battery-powered equipment, make impossible triage decisions. Water supplies are failing. Treatment plants require power. Pumps require power. Even if water is available, pressure is dropping. High-rise buildings, dependent on pumps to move water to upper floors, have no water above the 3rd or 4th floor. Sewage backs up. Sanitation collapses. Day 3. Food is running out. Grocery stores were emptied in the first hours. Home supplies, for most people, last a few days at most. hunger becomes widespread. In rural areas, with farms and livestock, people fare better. In cities, with millions of mouths and no way to transport food, starvation looms. Violence is increasing, looting, break-ins, fights over resources. Police, also without power and communications, cannot maintain order. Some jurisdictions implement martial law. Others descend into chaos. The social contract, built on the assumption that basic needs will be met, frays and breaks. Day 7, 1 week. The death toll, impossible to count accurately without communications or functioning systems, is estimated in the millions. Most from cold in winter regions, from heat in summer regions, many from lack of medical care, some from violence. The causes vary, but the fundamental issue is the same. Modern civilization requires electricity. Without it, people die, and the power is still not on. Because the transformers are not repaired, they are destroyed, windings melted, cores damaged, oil leaked. These components cannot be fixed in the field. They must be replaced, and each one takes months to years to manufacture. Engineers assess the damage. In the United States alone, 300 high-voltage transformers failed. Canada lost 100. Europe lost 400. Asia, with less robust grid infrastructure, lost thousands. The global manufacturing capacity is perhaps 50 transformers per year. Do the math. If every manufacturer on Earth works at maximum capacity, producing only replacement transformers, it would take a decade or more to replace what was lost. Week 2. Refugees are streaming out of cities. Millions of people, realizing that cities cannot support them without power, are moving to rural areas. Roads are clogged. Vehicles run out of fuel and are abandoned. People walk, carrying what they can. The migration is chaotic, desperate, deadly. Week 4. 1 month. Governments, what remains of them, are trying to establish order. Some regions have restored limited power using surviving generators and intact transmission lines. These become havens, attracting refugees, overwhelming local resources. Other regions remain dark, lawless, Hobbesian. Life in these areas has reverted to pre-industrial conditions, but without the knowledge or infrastructure to support it. The global death toll is now estimated at 50 million. 50 million! More than World War I, approaching World War II, and climbing. Because famine is setting in. Agriculture, dependent on mechanized equipment, fuel and distribution networks, has collapsed. The food that exists cannot be moved to where it is needed. People in one region starve while food rots in another. Month 3. The crisis has become the new normal. Electricity for most of the world is a memory. Survivors have adapted. Small communities, organized around local resources, function at a subsistence level. Larger population centers are mostly abandoned, too dangerous, too resource poor. International cooperation has ceased. Each nation, each region is focused on survival. Trade has stopped. Financial systems are irrelevant. Money, backed by governments that no longer function effectively, is worthless. Barter economies emerge. The satellites remain dark. GPS is gone. Communications are local only, using whatever radio equipment survived and can be powered. Weather forecasting dependent on satellite data is primitive. Hurricane warnings are reduced to hours instead of days. Blizzards arrive with minimal notice. The death toll from weather-related disasters increases. Month 6, half a year. The world is unrecognizable. Population is down perhaps 10%. Some estimates are higher. Cities are ruins. Governments, where they still function, control only limited territories. Most of humanity lives in small communities, farming, scavenging, surviving. And the question everyone asks in those communities, in those moments when survival allows for reflection, is whether this is permanent, whether the world they knew is gone forever, whether their children will grow up in a dark age, telling stories of a time when lights came on at the flick of a switch and people could talk to anyone anywhere, and machines did the work. Year 1. The answer slowly becomes clear. Recovery is possible. But it will take decades, a generation, perhaps 2. The knowledge still exists. Engineers know how to build transformers, how to string power lines, how to generate electricity. But the industrial base needed to manufacture these things at scale is gone. Factories were powered by the grid. When the grid failed, the factories stopped. Rebuilding them requires power, but power requires the equipment those factories produce. It is a catch-22, and breaking it requires starting small, rebuilding piece by piece, powering local areas, expanding gradually. The process has begun in some regions. Others remain dark and may stay that way for years. This is what tomorrow could look like if a Carrington-class storm strikes. Not science fiction, not exaggeration. A straightforward extrapolation based on known vulnerabilities, known dependencies, and known storm physics. The only unknowns are the timing and whether we will be ready. Why power grids are more vulnerable than ever before. The power grid was not designed for geomagnetic storms. This is a fundamental truth that engineers understand but the public rarely considers. When electrical systems were first developed in the late 19th and early 20th centuries, space weather was not a known phenomenon. The Carrington event happened in 1859, before widespread electrification. The telegraph disruptions were noted, but the implications for future electrical infrastructure were not considered. As grids expanded through the 20th century, they grew larger, more interconnected, more complex. Transmission lines stretched hundreds of miles. High-voltage lines, carrying power across vast distances, became the backbone of modern electricity distribution. And these long lines, these continental-scale conductors, are precisely what makes grids vulnerable to geomagnetically induced currents. GICs flow through the path of least resistance. In the ground, electrical currents induced by geomagnetic disturbances follow the geology. Rock conductivity varies. Sedimentary layers conduct differently than crystalline basement. The induced currents flow horizontally, seeking paths through the earth. When they encounter a grounded conductor like a power line, they flow into it. And once in the power transmission network, they travel along the lines, entering and exiting through transformer neutrals. Transformers were designed for alternating current. 60 Hz in North America, 50 Hz in most of the rest of the world. The magnetic field in the transformer core rises and falls with this frequency. But GICs are quasi-direct current, 0 Hz. When quasi-DC flows through a transformer winding, it biases the magnetic field. Instead of oscillating around 0, the field oscillates around some offset value. This causes 1/2 of each cycle to drive the core into saturation. When a transformer core saturates, it cannot support additional magnetic flux. The inductance drops. Current increases dramatically. The transformer overheats. Gases are released from the insulating oil. The structure vibrates. If the condition persists, windings can melt, insulation can fail, the transformer can be permanently damaged. This is not theoretical. It happened in Quebec in 1989. A geomagnetic storm induced currents in the Hydro-Quebec system. 7 protective relays tripped in less than 2 minutes. The grid collapsed. 6 million people lost power for 9 to 12 hours. One large transformer at the Manicouagan complex was damaged, though not destroyed. The event was a wake-up call. It demonstrated that geomagnetic storms could crash modern power grids. But here is the critical point. Grids today are more vulnerable than they were in 1989, not less, more. Why? Several reasons. First, the grid has expanded. More transmission lines, longer distances, higher voltages. The United States grid, for example, has grown significantly in the past 3 decades. New wind farms in remote areas require long transmission lines to connect to load centres. Solar farms similarly need transmission infrastructure. The renewable energy transition, laudable for many reasons, has increased the total length of high voltage lines, which increases GIC vulnerability. Second, the grid has become more interconnected. In the past, regions had more electrical independence. Local generation served local load. Today, power is bought and sold across wide areas. The Western interconnection spans from Canada to Mexico. The Eastern interconnection covers everything east of the Rockies. These interconnections allow efficient power sharing, but they also mean that disturbances propagate. A problem in one area can cascade to others. A GIC event affecting multiple transformers simultaneously could trigger a widespread collapse. Third, the grid is more heavily loaded. As electricity demand has grown, grids operate closer to capacity. There is less margin, less ability to absorb unexpected stresses. In an earlier era, a transformer going offline might be compensated by others with spare capacity. Today, losing a major transformer can immediately stress the surrounding network. And if GICs are affecting multiple transformers at once, the stress accumulates rapidly. Fourth, transformers are aging. The average age of high-voltage transformers in the United States is over 40 years. Many were installed in the 1960s and 70s. They have exceeded their design life and are maintained through careful monitoring and maintenance. But old transformers are more vulnerable. Insulation degrades. Cooling systems become less efficient. The ability to withstand abnormal stresses decreases. A GIC event that a new transformer could handle might destroy an old one. Fifth, and perhaps most concerning, transformers are harder to replace. Modern high-voltage transformers are enormous. They weigh hundreds of tons. They are transported by specialized rail cars and require custom infrastructure to move and install. Each one is built to order, customized for the specific substation where it will operate. Lead times are measured in years, and the global manufacturing capacity is limited. Perhaps a dozen facilities worldwide can produce the largest units. If multiple transformers fail simultaneously, replacement becomes a logistical nightmare. You cannot simply order more from a warehouse. You enter a queue. You wait years. And during that time, the grid operates with reduced capacity, more vulnerable to cascading failures, less able to serve load. There have been efforts to address these vulnerabilities. After the Quebec blackout, utilities began installing monitoring equipment to detect GICs in real time. Some substations added series capacitors or resistors to block quasi-DC flow. Transformer design improved slightly, though the fundamental vulnerability remains. And grid operators developed protocols for solar storm warnings, procedures to shed load and isolate vulnerable equipment when major storms approach. But these measures are incomplete. Not all utilities have implemented them. Budget constraints, regulatory priorities, and the rarity of major storms all work against comprehensive preparation. A survey of United States utilities found significant variation in readiness. Some large transmission operators have robust space weather programs. Smaller utilities serving rural areas may have minimal awareness of the threat. There is also the question of whether the protective measures are adequate for extreme events. The equipment installed, the protocols developed, these are calibrated to storms like the one in 1989 or the May 2024 event. But a Carrington-level storm is an order of magnitude stronger. The GIC levels could exceed anything the protective equipment was designed to handle, and at some point, you cannot engineer your way out of the problem. You can only reduce the damage. Geography matters too. Regions at high latitudes are more vulnerable because geomagnetic disturbances are stronger near the poles. But geology also plays a role. Areas with resistive bedrock like the Canadian Shield experience higher GIC voltages. The rock does not conduct well, so more current flows into the power lines. Coastal areas, with conductive seawater nearby, can have complex GIC patterns. Some utilities are more at risk simply because of where they are located. The 1989 Quebec event demonstrated another vulnerability: cascading failures. When one part of the grid goes down, load redistributes. Other components become stressed. If they fail, more redistribution occurs. And if enough components fail quickly enough, the entire system collapses. This is not unique to geomagnetic storms. Cascading failures have occurred in other contexts, like the 2003 Northeast blackout. But GICs add a complication. They affect a wide area simultaneously. Normal cascades start at a point and propagate. GIC cascades can start everywhere at once. Grid operators have protection schemes to prevent cascades, automatic systems that disconnect regions, isolate problems, maintain stability. But these systems were designed for normal faults, short circuits, equipment failures, generator trips, events that are localized and follow known patterns. A GIC event affecting hundreds of transformers across an entire continent does not fit the pattern. The protection schemes may trigger inappropriately, cutting off power to regions that did not need to be disconnected, or they may fail to trigger when needed, allowing the cascade to continue. There is also a human element. Grid operators, monitoring their systems in real time, make decisions based on what they see. But during a major geomagnetic storm, the situation is chaotic. Alarms are going off everywhere. Systems are behaving abnormally. Communication with other utilities needed for coordination may be disrupted. And the operators, under enormous stress, must make critical decisions with incomplete information and limited time. Mistakes will happen, and some of those mistakes will make the situation worse. After the November storm, when the dust has settled and the data has been analysed, engineers will study what happened, which transformers experienced high GICs, which protective systems worked, which failed. Lessons will be learned, reports will be written, recommendations will be made, but the fundamental vulnerabilities will remain. Long transmission lines, aging transformers, interconnected systems, limited spare capacity. These are features of the modern grid, not bugs. Fixing them would require massive investment and decades of work. Some researchers have proposed radical solutions. Distributed generation, where power is produced close to where it is used, reducing the need for long transmission lines. Microgrids, where communities can disconnect from the main grid and operate independently during emergencies. High voltage DC transmission, which is immune to GICs because it does not use transformers in the same way. Energy storage, using batteries or other technologies to provide backup during grid outages. These are good ideas. Implementing them would make the grid more resilient, not just to geomagnetic storms, but to other threats as well. But they require political will, regulatory changes, and enormous capital investment. Utilities, operating on tight margins and focused on quarterly returns, are reluctant to spend money on rare events. Regulators, balancing many priorities, hesitate to mandate expensive upgrades, and the public, unaware of the threat, does not demand action. The result is a grid that is functional under normal conditions but brittle under stress, a system optimized for efficiency, not resilience. A network that works beautifully when everything goes right but can collapse catastrophically when things go wrong. And geomagnetic storms by their nature make things go wrong everywhere at once. The Quebec blackout was a preview. 12 hours of darkness, minimal damage, recovery in days. But it was caused by a moderate storm. A strong storm like the November event might cause longer outages, more damage, slower recovery. And a Carrington-level storm. The grid might not come back at all, at least not for months or years. Engineers know this. Space weather researchers know this. Government agencies know this. The information is not secret. Reports have been published. Hearings have been held. Studies have been commissioned. Everyone agrees that the grid is vulnerable and that a major solar storm could be catastrophic. But knowing and acting are different things. Knowing requires understanding a problem. Acting requires resources, authority, and urgency. And urgency is hard to generate for a threat that may not materialize for years or decades. There is always something more pressing, always a crisis demanding immediate attention. And so the vulnerability persists, the grid remains fragile, and we hope, quietly, that the next big storm does not come before we are ready. What if we can't rebuild? In time, there is a concept in systems theory called resilience. It describes not just the ability to withstand shocks, but the ability to recover from them. A resilient system can absorb damage, adapt, and return to functionality. A brittle system, by contrast, might survive small shocks, but collapse completely under larger ones, and once collapsed, it may not be able to rebuild at all. Modern technological civilization is brittle. We have optimized every system for efficiency, removing redundancy, minimizing waste, maximizing productivity. Just-in-time manufacturing, lean supply chains, interconnected networks. These practices work beautifully under normal conditions. They reduce costs, increase speed, enable the complex global economy we depend on. But they eliminate buffers, and buffers are what allow recovery. Consider what happens if a Carrington-level storm destroys a significant fraction of the power grid. Not just causes a blackout, destroys, melts transformer windings, cracks insulation, physically damages the infrastructure to the point where it cannot be repaired, only replaced. Now ask yourself, where do replacement transformers come from? They are manufactured in factories that require electricity. The very thing we need to rebuild is the thing we need in order to rebuild. This is the core problem. The grid enables industrial production. Industrial production enables grid repair. If you lose both simultaneously, how do you restart the cycle? Some facilities have backup power, generators, fuel reserves, enough to keep critical systems running for days or weeks. But transformer manufacturing is a long-term process. It takes months to produce a single large unit. Months of continuous operation, smelting steel, winding copper, assembling cores, testing. Every step requires power, skilled labor, specialized equipment. A generator running for a week does not help if the grid is down for a year. There is also the supply chain problem. Transformers are not made from raw materials on site. The copper comes from mines, the steel from mills, the insulating oil from refineries. Each of these industries requires power, transportation, coordination. If the storm has knocked out grids globally, if transportation networks are disrupted, if coordination is impossible because communications are down, then even facilities with backup power cannot manufacture transformers because they lack materials. Some researchers have modelled this scenario. They call it systemic collapse. Not just a temporary setback, not a recession or depression, a fundamental breakdown of the industrial economy. And their conclusion, based on rigorous analysis, is that recovery might not be possible, at least not recovery to pre-collapse levels. The civilization that emerges from such an event might be permanently poorer, simpler, less capable. Think about what we lose if the power is out for a year. Food production and distribution systems collapse, leading to famine. Medical systems fail, causing preventable deaths. Water treatment stops, spreading disease. Social order breaks down in many areas, leading to violence. Population declines significantly, and the survivors, focused on immediate survival, are not working in factories or research labs. They are farming, scavenging, defending territory. After a year, even if some regions manage to restore power, the global industrial base is shattered, the workforce is depleted. The knowledge base, while not entirely lost, is degraded. Experts die, retire, or are unable to work. Written records may survive, but tacit knowledge, the kind that exists in the minds of experienced engineers and technicians, disappears. and rebuilding complex industrial systems requires both. There is historical precedent for this kind of collapse. The Bronze Age collapse around 1200 BCE saw multiple advanced civilizations in the Eastern Mediterranean fall within decades. Trade networks disintegrated. Cities were abandoned. Writing systems were lost. The region descended into a dark age that lasted centuries. The causes are debated, but the result is clear. Complex societies can fail, and when they do, recovery is slow and uncertain. Modern civilization is far more complex than Bronze Age societies. We have more technology, more knowledge, more capability. But we are also far more dependent on that technology. Bronze Age people could farm without electricity. They could communicate without satellites. They could navigate without GPS. We cannot. Or rather, we have lost the skills and infrastructure to do so. How many people know how to grow food? How to purify water? How to build shelter without modern tools? The percentage is tiny. If a Carrington storm forces a return to pre-industrial conditions, most of the population lacks the knowledge to survive, and even those who do face enormous challenges. Pre-industrial agriculture supported much smaller populations. The land can only sustain so many people without fertilizers, pesticides, mechanized equipment. Current global population is 8 billion. Pre-industrial agriculture might support 1 or 2 billion. What happens to the rest? Some argue that this scenario is too pessimistic, that human ingenuity will find solutions, that even in the darkest times people adapt, innovate, overcome. This is true to an extent. Humans are remarkably resilient. But there are limits. Innovation requires resources, time, stability. In the chaos following a major collapse, those conditions may not exist. There is also the question of how fast critical infrastructure degrades. Power grids, if not maintained, deteriorate. Transmission lines corrode. Transformers, even if not in use, degrade over time. If you cannot restore power within a few years, the equipment you are trying to reconnect may no longer be functional. The window for recovery narrows. Eventually it closes, and then there is the geopolitical dimension. Not all regions would be affected equally. Some areas, due to latitudes, geology, or grid design, might fare better if those regions recover while others remain in chaos. What does that mean for global power dynamics? Do the recovered regions help the others, or do they exploit them? History suggests both are possible, often simultaneously. Nations that maintain order and rebuild quickly would have enormous advantages. They could dominate trade, control resources, exert influence. Nations that collapse into anarchy would become sources of refugees, instability, conflict. The post-storm world might be more fractured, more competitive, more dangerous than what we have now. Climate change adds another layer of complexity. Recovery from a major collapse would require enormous energy expenditure. Rebuilding infrastructure, restarting industry, feeding populations. In a world already facing climate stress, where would that energy come from? Fossil fuels are the obvious answer, but burning them at the rates needed for rapid rebuilding would accelerate warming. Renewable energy requires intact supply chains and functioning grids to deploy. The cleanest recovery path requires the very systems that the storm destroyed. Some futurists suggest that a major collapse might force humanity to rethink its relationship with technology, to build systems that are more resilient, more sustainable, more attuned to natural limits. This could be a silver lining, a forced reset that leads to better outcomes in the long term. But that assumes we survive the transition, and there is no guarantee we will. The archaeological record is littered with collapsed civilizations. Societies that grew complex, thrived for centuries, then disappeared. Sometimes slowly, sometimes suddenly. The reasons vary. Environmental changes, resource depletion, external shocks. But the pattern is consistent. Complexity is fragile, and once lost, it is very difficult to rebuild. We like to think we are different. that our technology makes us immune to the forces that toppled earlier civilizations. But technology is not immunity. It is dependence. We have built a world that functions only if multiple complex systems work simultaneously. Power, communications, transportation, financial networks, food distribution, medical care. Each depends on the others. Each is vulnerable. And if they fail together, the cascade could be unstoppable. This is not to say collapse is inevitable. It is not. With adequate preparation, with hardened infrastructure, with robust response plans, with a culture of resilience, we can survive even major solar storms. Other nations have made progress. Japan, accustomed to earthquakes and tsunamis, has built considerable resilience into its systems. Some European countries have invested in grid hardening. These efforts matter. They reduce risk. They increase the probability of recovery. But globally, preparation is uneven. Many nations, including some of the most technologically advanced, have done little. The United States, despite having some of the world's leading space weather, research has not comprehensively hardened its grid. China, building new infrastructure rapidly, has opportunities to include protections but faces cost pressures. India, with massive population and growing energy demand, has limited resources for resilience investments. And so we enter each solar maximum with fingers crossed, hoping the big one does not hit, hoping that if it does, it hits when we are as ready as we can be, hoping that response systems work, that people cooperate, that recovery is possible. Hope is not a strategy. But for many aspects of space weather preparedness, it is what we have. The storm that passed yesterday was a reminder, a warning shot. AR4274 showed us what the sun can do. Ground-level radiation, G4 conditions, cannibal CMEs. It was not the worst case, but it was a taste, a preview of what could come, and the truly sobering thought is that the next storm could be worse, much worse. And it could come not years from now, not decades from now, but tomorrow, or next week, or next month. The sun does not schedule its eruptions for our convenience. It does not wait until we are ready. It simply does what the physics dictates, releasing energy in bursts, hurling plasma into space, and sometimes, by chance or by cosmic coincidence, aiming that plasma directly at us. We have built a remarkable civilization. Lights that turn on instantly, information flowing at the speed of light, food transported across oceans, medicine that extends lifespans, comforts and capabilities that would seem like magic to our ancestors. But all of it, every last bit of it, depends on systems we cannot fully protect. The sun is 150 million kilometers away, a giant fusion reactor converting 4 million tons of mass into energy every second. It has been doing this for 4.6 billion years. It will continue for billions more. And occasionally, through processes we understand but cannot control, it releases a fraction of that energy in our direction. When that happens, when the next Carrington event occurs, we will discover whether our civilization is resilient or brittle, whether we can adapt and recover, or whether we collapse, whether the lights come back on in weeks, or whether they stay dark for generations. The answer will determine what kind of world our children inherit, and that answer depends in large part on what we do now, today, in the brief window between storms, when we have time to prepare but often lack the will to act. The choice is ours. The sun will do what it does. The only question is whether we will be ready.